if just magically you snapped your fingers and the sun was a black hole, we could just orbit completely safely. In fact, you can't get within 1.5 million kilometers of the sun, right? It's the center of the sun. You'd be incinerated. So the sun's much more hostile than the black hole. I could get 30 kilometers outside a black hole.
That is
30.
so cool.
Yeah.
So
I could get right on top of it.
Star sun is more malignant than black hole sun.
Yeah, for sure. You could orbit very close to a black hole and be perfectly safe if you had your own little unit, nice little space station with all your amenities.
What's up, y'all? Today, I sat down with Janna Levin. She's an astrophysicist who's an expert on black holes. And who doesn't want to hear about black holes? You might have seen her hosting the Nova film, Black Hole Apocalypse, and she's written a bunch of books on the subject, including her latest, Black Hole Survival Guide. She's a professor of physics and astronomy at Barnard College and the founding scientific director at Pioneer Works, which is this really cool artist and science-led nonprofit cultural center. We talked about some of the biggest misconceptions people have about black holes, how weird black holes can be, and how scientists actually go about detecting them. This conversation bent my space-time. Now, if you feel attracted to this content, gravitationally or otherwise, please rate us, leave a review, or drop us a comment. Make sure to subscribe so you can catch every episode. Your support means everything and helps us reach more curious minds like yours. Now let's get it. Welcome, Janna.
Thank you. I'm glad to be here.
Yeah. So I did a little background research and realized that you and I are born in the same year.
No way. You're not allowed to tell people that.
Right, we're both like 26. So here is something that I wonder if we have in common since we're from the same generation. When I was in high school and college and I was asked to write an essay, I realized pretty quickly that if I wrote my essay about black holes, I would get an A because the teacher had no idea. In fact, I did my senior thesis on energy extraction from a black hole. So did you use the same technique?
Was this high school?
No. In high school, just that they exist.
Yeah.
I found a book in the library at college, and so I'm like, So you use the same trick? Or?
Oh, I think I just fell into black holes. It's, metaphorically speaking.
Okay, I'm like pun intended?
I didn't start studying science until about halfway through college.
Oh.
I didn't start studying physics.
Okay, were you a science major?
Math and physics. No, I was a philosophy major. I was so misguided.
Well, I don't know. That's,
completely,
still deep thinking,
I liked the
right?
big questions, exactly. That's really it. It's the big questions. And then I kind of accidentally discovered physics and realized that this had this transcendent power and that it was true for everybody.
How did it
Nobody
happen?
was arguing about what somebody meant anymore. Nobody's like, what did Einstein mean? I can't. Because you can learn it and it's yours.
Yeah,
I thought that was
right.
incredible.
Right. Yeah,
and you can teach it to somebody else.
Yeah.
And it can propagate through the world that way. I was completely overwhelmed with the power of that. Whereas people were still arguing about philosophers from 400 years ago, what they might have meant. And I just thought, it could not have been that important then.
Well, or they don't know what they're doing, right? There isn't an answer. Because that struck me, what you just said. When you're young, you're having these debates about religion and politics, right? I would point out to people, I was like, there's something about science that's different from religion. And that is that it's the same everywhere on the planet. It's not like you go to Saudi Arabia or you go to India or you go to China and suddenly there's a different version, right?
Yeah, absolutely. Ramanujan can come out of a small town in another continent and reinvent ways of calculating pi.
Wow.
It's just true.
Yeah, it's just true. It just
true.
is. Yeah.
And so I do love that about math and physics.
So let's get into black holes.
Right.
So when we think about a black hole, I think that, in a second we're going to define what it is. But I think one of the things that is not appreciated is how small they are. So if the sun were a black hole, it would be something like 2 miles or something.
Yeah,
right?
I mean, I'm still stuck in kilometers. It would be 6 kilometers across.
Oh, 6 kilometers across.
I give that to me in miles. I don't know.
Yeah, so if you saw an asteroid that's 6 kilometers, that's a tiny asteroid.
That's a tiny object. That would fit inside Manhattan.
So you wouldn't even see it
Before
as
it
you're
consumed
approaching
Manhattan.
it, right? If you were out in space and stars all around, you wouldn't even notice a little a sun-sized black hole.
Yeah, black holes are notoriously hard to detect because you can't resolve them. They're too tiny.
Yeah.
Think of a star on the sky twinkling, and those are millions of kilometers across, millions of times bigger, and they're just a twinkling speck.
Right.
How are you going to see something emitting no light, reflecting no light, that's only 6 kilometers across at such a great distance? You're not.
You're not, even at a close distance.
Yeah,
Right?
and people, I think, were very surprised that we had never taken a picture of a black hole before this century. So when we were talking about detecting black holes, it was all indirect, very well deduced, very compelling, very convincing, but we didn't have a picture of one. And that's only been in the last few years.
Let's get into the reputation of black holes because, you know, if you watch Interstellar, you know that they do some nasty things, like they can make you older than your children.
Right.
Younger than your children.
They can
make you younger than your children. Then there's this notion that they just suck everything in. So once upon a time, ABC News called me science's greatest hype man. But you're the PR agent for black holes. So are they as bad?
Yeah, I think they get a bad reputation. So they're not these weapons of destruction that they're portrayed to be. I like to do a little myth busting about black holes. One of the first myths is that black holes will destroy everything in the universe, and actually, you leave them alone, they'll leave you alone. You know, they're
kind of like honeybees.
They're quite benign in a lot of ways. So if the sun were to turn into a black hole tomorrow, I mean, it would be terrible. We would lose our life force. It would get cold. But our orbit would be pretty much the same. Our orbit would be fine. So we wouldn't get sucked into the sun.
So the planets wouldn't get, Mercury wouldn't get sucked in.
No, I mean, if just magically you snapped your fingers and the sun was a black hole, we could just orbit completely safely. In fact, the sun is 1.5 million kilometers across, right? And so you can't get within 1.5 million kilometers of the sun, right? Get to the center of the sun. You'd be incinerated. So the sun's much more hostile than the black hole. I could get 30 kilometers outside a black hole.
That is
30.
so cool.
Yeah.
So
I could get right on top of it.
Star sun is more malignant than black hole sun.
Yeah, for sure. You could orbit very close to a black hole and be perfectly safe if you had your own little unit, nice little space station with all your amenities. You could just sit there and watch it unfold.
You just flip the universe, right? Because everybody thinks black hole, star.
Right.
Which hurts most?
Right.
You think black hole.
Yeah.
But the answer is no, star.
No, and in fact, the bigger the black hole, the kind of safer you are. If you fall across a very big black hole, you won't feel squeezed, stretched, torn apart, spaghettified. None of that stuff will happen to you until you start to get towards the center.
Until you get to the very
I mean,
close.
Then it gets pretty bad. I mean, there's no surviving.
Well, it depends. You know, what if you flex?
It's going to be stronger than you.
Is it stronger than your molecular bonds and your atomic bonds?
Right, but think about, you just flex. Think about how weak the Earth is. The entire mass of the Earth, that whole gravitational field of the entire planet is pulling on you right now. But I can lift my little arm. You know?
Right. Yeah,
no
you're strong enough
problem.
to go in the opposite direction.
Look at this. Look at me.
Yeah, right. Wow.
But if you were on a neutron star, which is a dead star that did not quite become a black hole, it is a dense object. But it does not have an event horizon. Light can escape. We do see neutron stars with light. But they are so dense that, let's say they're 20 kilometers across instead of just 6 or something. They're still so dense that you'd be liquefied because you could not lift your arm up. Your atoms, you could not flex. You could not stay bound together. Just gravity would totally pull you apart.
So several months back last fall, I got to ride the Vomit Comet, the zero-G plane.
Oh, wow.
And zero-G was fascinating, but what I found really fascinating was when you were going up and you were at 2 Gs.
Right.
I never experienced that, you know, and
it's a lot harder to move around.
Yeah, it's hard to move around.
Right, when you increase the equivalent acceleration.
Yeah, so because I started puking, I was no longer lying flat. I was back in a chair, strapped in with my bag. Yeah.
Gosh, terrible. That's why I won't do it.
But I got to do all these gravity experiments back there, and that was so weird to me. Weirder than
than the zero G. Well, zero G I can achieve by jumping off the table.
Right.
It just doesn't last very long.
Yeah.
So Einstein called this the happiest thought of his life. When he realized, I feel heavy on this chair. I can't get out of bed. So that's not gravity. That's actually you pushing off the atoms in your chair, in your bed. This idea of the thought experiment, removing effects that don't belong in your experiment. He said, let's just remove the chair. Let's remove the floor. Let's remove the ground. What happens? Then you're just falling.
Yeah.
And he called it free fall.
Yeah.
And you feel weightless, actually.
Wait a minute. Did he coin that phrase?
Oh my God. I've never thought about it. He didn't say free fall.
I don't know.
Now we need a history check.
Yeah, now we need, because sometimes you learn where the phrase came from. It's typically Shakespeare, but
right. Maybe it was Shakespeare or Dante.
Or Flavor Flav.
Well, I would have thought it was Einstein, but I guess I've never actually checked. But the concept that you will experience weightlessness if you remove everything except gravity is very profound. So zero G's, this idea that I have to go up in blue origin and break the Kármán line where the atmosphere thins out in order to experience no gravity. No, that's nonsense. That makes no sense at all.
Yeah.
All that's happened is you're falling and you get more fall out of a greater height than if you jump off the table.
Yeah, so
and you crash on the floor
longer.
immediately. It lasts longer, and you get to do a little parabola right before you have to scoop up again. But you can get zero G under earthly circumstances. When you're at the Kármán line, where things like blue origin are skirting, you are absolutely being pulled on by the earth.
Yeah.
You do not want to drop like a stone and hit the surface of the earth, because
you
you will. Right? You're not going to drift off. So the International Space Station is another great example. They're very much under the pull of the earth.
Otherwise, they just
they're not floating away. They're bound to the earth. They keep falling towards the earth. In fact,
just missing it.
They're just missing it. That's exactly what they're doing. They're cruising so fast, 17,500 miles an hour, that they clear the horizon. They just never actually crash into the crust.
Yeah.
But they are very much experiencing gravity. Earth's gravity, and if you were to stop it from cruising at 17,500 miles an hour, it would drop like a stone.
So before we go further, let's define what a black hole is. Let's do black hole 101.
Right.
Tell the audience how you define a black hole.
Yeah, I think there's many different ways to approach it.
Yeah.
Most people will say an object so dense that not even light can escape.
Yeah.
And there's good things about that description. There's really bad things about that description. So a good thing about the description is that it captures one of the most fundamental attributes of the black hole, and that is that it goes completely dark. Yeah. Nothing will ever escape, not even light. And so that part is the crux, in some sense, of what a black hole is. Okay. We say that around the black hole, we circumscribe it with the region around which light can no longer escape. We call that the event horizon.
Yeah.
What's bad about that description is that there's nothing there. There's no dense object
at the event
horizon, right? So I don't like the image of a thing, a thing, right?
Yeah.
That's just really, really dense. Now, it's true, often black holes are made by dense things on their way out.
Right, yeah.
But at the event horizon, where the light is forced to fall in, there's just empty space. Wow. So the black hole is just a space-time.
A volume of space.
Right. It's just, it's more of a place in some sense than a thing. Yeah. So I can go up to this event horizon, and if I'm trying to shine a flashlight and I'm shining light, the light, as I get closer, will be trapped in orbit at some point around the black hole. And then eventually, as I get closer, it won't even be able to do that anymore.
It's just going straight in.
And it's just going straight in, as am I.
Right.
But I don't bump into any matter. I don't smack into any surface. I just sail across an empty space. Yeah. So what are black holes?
How disappointing.
Well, I mean, honestly, you might not even notice anything bad was happening to you.
Yeah.
It would be no more dramatic in some sense than stepping into the shadow of a tree. It's just a shadow.
So suddenly
but
you're
for
cut
you,
off.
Yeah. So if you say, what is a black hole? I would say the black hole is really the event horizon.
Okay.
It's this horizon beyond which light cannot escape.
If you're looking out, you can see light coming in though, right?
That's right. So if you fall in, it can be bright on the inside because the light can fall in from all the stars shining, all the galaxies, all
Yeah.
of that can fall in behind you. And you can see all of this happening. So it can be right on the inside. It's just dark on the outside.
So let's do an
It's a
experiment.
it's a one-way transition.
So suppose the light's coming in toward you and
Yeah.
you hold up a mirror to reflect the
Yeah.
light back out. What happens?
It's tricky because we're standing on the outside of a black hole, let's say.
Yeah.
And we're throwing that light in, and your companion has fallen in
Right.
ahead of you. We are imagining that interior to that event horizon, that
Right.
is a spatial direction. I mean, all our intuition says it. It says once you cross inside, there's a spatial direction pointing towards the center of
Right.
a point in space.
Yeah.
But space and time are relative.
Okay,
And to the
absolutely.
observer who has
Yeah.
fallen inside, they are very rotated relative to your space and time. What they're calling space and what you're calling space are now very misaligned. And so that direction for the observer who fell in, that points towards what we sometimes call the singularity,
Yeah.
that is a direction in time now.
Right.
So the person falling in can no more bounce the light that comes in behind them back out than they can bounce the light backward in time.
Wow.
So there is no such option to
There
do
is
that,
no
nor
such
would they
option.
imagine such an
Wow.
option, because to them, they and the light are continuing to fall forward in time, and that is driving them in the same direction towards the center.
So let me create
So
an
it's
analogy.
tricky. I'm not
Is
saying
it like
it's,
refraction, like where you see the spoon in the water, and so this was going in that direction, but now it looks like it's somewhere else, it's disconnected, but it's more extreme?
Yeah, I mean,
So the event horizon would be like the surface of the water.
yeah, I would say you can bounce the light in different spatial directions,
Yeah.
just that direction is no longer space at all. So, it really is,
wow.
it really is in your past,
Yeah.
the event horizon. So there's no even turning around anymore, and the light can fall in behind you, you can see things, but you can't claw your way back, nor can you send anything back that way. Now, if you could travel back in time, we could get tricky and start to talk about things like that. But then you're doing stuff on the outside that's pretty crazy too.
So we talk about the strong gravity.
Yeah.
And so we usually speak in terms of space, curvature of space
Yeah.
and time.
Yeah.
So is it possible to curve time in such a way that you move backwards in time?
Oh, well, I can definitely move to, for instance, someone's future
Right.
by rotating space and time or bending space and time.
Yeah.
We don't yet know of a way for me to travel to my future.
Right.
But I can travel to yours.
You can travel to mine.
I could go in a rocket ship,
That
travel
was
near the speed of light.
romantic, by the way.
You said we're born in the same year.
Yeah.
I could come back 10 years your time, 2 minutes my time. Right. I mean,
Beautiful.
technologically, I
Right.
can't do it.
Right.
But
But
physics allows
it's
it.
possible by the rules
And
of the
particles
universe.
do this. Light things can, not heavy things,
Right.
things that don't have a lot of mass, can do things like that. So I could go travel in a rocket ship, go towards Alpha Centauri near the speed of light, double back, and I'll be 2 minutes older and you'll be 10 years older. So really, the idea is that as I get faster and faster towards the speed of light, it's as though time stands still altogether, and your clocks are elapsing hardly at all. They're barely ticking, and this is one of the deep ideas in relativity, sometimes called time dilation, that time is not absolute, and it matters what path you're on in space-time, what we call your world line.
This phrase we use all the time,
Yeah.
the age of the universe.
Yeah.
There is no such thing
Right.
because it's all relative.
Oh, well, that's an interesting question. I would say you can very well define the age of the universe in the following way. You can say for an observer
Yeah.
who's not moving a lot relative to the expansion of the universe, right? So we're not
Right.
zipping
You're
around in
at rest relative
rockets.
to the expansion,
Yeah,
yeah.
we're just kind of as though you drew a dot on space-time and stretched the space-time, but you're a bit of ink. You're a
still in that
stain,
coordinate.
and you haven't moved. You're just stained on the space-time. Then you can very well define, according to the clocks of all of those observers, just like you, all over the universe or the observable universe, that it is 13.8 billion years ago that this primordial event happened that we call the Big Bang. We're all going to agree on that because we're all in a very similar
Yeah, but what if
kind
you
of
travel
world line.
so fast
Yeah.
that a billion years passes for me, but 2 seconds pass for you.
Yeah. Now, I would say, right. So you would say, yes, I have not.
You've moved yourself off that
I've
position.
moved myself off of that, and I understand, though, why everyone else is claiming the universe is a billion years older.
Yes,
So we can agree on that. We can
That's
say, yes, I understand why you all, in coordination, are arguing that the universe is 13.8 billion years, or if we've had another billion, 14.8 billion years, in a billion years.
But for the objects in the universe, they all have their own set clocks.
They can all have their own experience of the passage of time.
Wow.
And you can't think of it as a terrain. You experience the terrain differently. We know that this is real. We know it's not just your speed, but it can also be near the Earth or away from the Earth. So. Near heavy objects or away from heavy objects. They curve the whole space-time in a way that's unambiguous. So we know that our clocks run more slowly on the surface of the Earth than they do further and further away. And we see this effect in our satellites. Our satellites are doing two things. Our GPS units have to correct for the motion of the satellites around the Earth and their distance from the Earth, and
so
to get
it's
the
a
relativity
and gravity effect.
Right. I actually think the motion might dominate for some satellites, but you have to do both relativistic effects, and then and so the satellites have slightly different clocks, or their clocks are not synced with ours perfectly.
Man, that is wild. So they have to. They're moving relative to each other. They're moving relative to the ground. So that's a lot of calculations.
Right. And if you don't correct for it, then you're not going to find your Uber. There's no way you're going to find your Uber.
You.
Yeah.
All right. So here's a question I get. People ask me this all the time, and I think I have an answer.
Yeah.
But the question is, they say, look, if you take the estimated mass of the entire universe, when you do a calculation of the radius that you'd have to push that all into to turn it into a black hole, it turns out to be about roughly the size of the observable universe. So is the universe a black hole?
Yeah. No, I'd say the universe is not a black hole. There's different things. First of all, the universe is expanding, and so taking a step back, Einstein really said how matter and energy is distributed in space-time dictates how space-time curves.
Right.
And when we say, oh, I'm around a black hole and everything's going to fall in, we're kind of ignoring the fact that there's all this other stuff in the universe. When I look at the average of all the stuff in the universe on the largest scale, the solution to Einstein's equations, which would tell you if it was a black hole, it would tell you if this was a black hole, and it is not.
They say no.
The solution to an average amount of stuff, more or less the same, all over the observable universe, is that it's actually expanding. And in fact, if you look at all the matter in the universe, the mystery isn't that it's expanding, it's actually expanding faster than the mass can account for. And that's where people have heard this expression about dark energy. So we're deducing that there's something else out there that is contributing to the energy budget of the universe. And it's driving the space-time to expand ever faster. So it's getting faster and faster, not slower and slower, because you would kind of expect it to be getting slower and slower. It comes out of the Big Bang.
Because everything's all gravitationally attracted to each other.
Right. It's coming out of the Big Bang. It's expanding. Eventually, it could kind of just get to its maximum, feel all that mass and come back and collapse again. But that is not what's happening.
So I was a graduate student and I did X-ray physics and extreme ultraviolet physics. So there was this one bright object in the sky, Cygnus X1, this double star.
Amazing.
But then, we're looking at the light, we're interpreting the light, there must be a black hole there. But then we have Andrea Getz and her team measuring the stars moving around the center of the galaxy.
Right.
We have the Event Horizon Telescope imaging, this planet-sized radio telescope imaging black holes at the centers of galaxies, supermassive ones.
Right.
And then we get LIGO Virgo gravitational wave observatories.
Right.
This is nuts.
Yeah, this has been the century for black holes.
I
would say late part of the last century, people were kind of losing interest in black holes. It wasn't clear there was that enthusiasm that there is now. All of this has been driven by experimental and observational discoveries that happened this century.
As
pretty
it
amazing.
should be.
Yes.
Yeah, freaking Einstein spoiled us coming out with this theory,
Yeah.
right? But an observation and an experiment.
Yeah, I mean, it just gave people a lot more energy, and they were galvanized to understand these very difficult problems. And theoretically, black holes remain incredibly important, but they were real astrophysical objects. I mean, Einstein even accepted the math of black holes before he accepted their reality in the sky. He thought nature would protect us from such
Well, it
anathema.
does sound like a crazy thing to occur, right? Because it's so different from our experience.
But even more so, how are you going to crush something
That
so
big.
small,
Yeah.
right?
That big to that small.
Right. So how am I going to make the sun a black hole? I mean, I can't crush this cup. You know, in principle, this could be a black hole. It'd just be atomic sized.
Right.
But nobody can overcome the resistance of the matter.
Right.
So matter has its own forces, nuclear forces and quantum forces. Yeah, it does not want to be crushed.
No, it does not.
And we all know that it's very hard. You know, guys try to crush a beer can. You know?
Right.
They can only make it so
egg
small.
Experiment, right?
Yeah.
So here's the question. So what's next? So where is this going?
Yeah.
Because I feel like we're at the infancy of it in a way, right? Because these experiments are
I mean,
new.
if all of our science funding doesn't get cut, yeah. So we could be in the infancy of it. I mean, a lot of the experiments took many years, 20 years or 50 years.
Yeah.
I mean, LIGO, this experiment which detected two black holes in orbit around each other, which then collided and merged into one big black hole. And it was like mallets banging on a drum, the whole of space-time. Literally space and time
Just
ringing.
Yeah.
And that ringing emanated through the universe. In the particular case of our discovery, what was it? 1.5 billion years? Do I have that number right?
The first one? I don't know.
The first one. I feel like that's right.
It's 1.5 billion light years away?
Yeah.
Wow.
Like multicellularity was underway on the
my
Earth.
goodness.
Right?
Yeah, right.
And I mean, that's happening all over. But this was the one that we were on this collision course with it.
That is something.
And, you know, humans evolve. Einstein comes around and it's at a neighboring star system. It's still on its way here, ringing, space-time's ringing.
So Einstein showed up just in enough time for us to see it.
For us to detect this one. And by the time they built the detector and they...
well, go into it, because I don't think the people may know what LIGO is.
Yeah, so LIGO is the Laser Interferometric Gravitational Wave Observatory. It's a very cumbersome name. You don't even need to know. Just LIGO.
Just some mirrors and lasers.
To its friends.
Yeah.
It's an enormous instrument. It's shaped like an L, and it shines light down these long vacuum tubes, 4 kilometers long on each side. And what it's really doing, I liken it to a musical instrument. What it's really doing is it's delicately bouncing these mirrors so that if a wave passes in the space itself, the mirrors will like bob with the wave.
Yeah.
And then the distance traveled along the 2 directions is going to be modulated by this bobbling. And the entire experiment is designed to detect motions like that of less than a 10,000th the width of an atom across 4 kilometers. It was the most stunning engineering achievement. I mean, even if it hadn't detected anything, it would have been really sad. But as an engineering achievement, it was tremendous. It took 50 years.
Wow.
And so you imagine that when they finally installed the advanced components of this detector, they'd been running for 15 years with an initial detector that detected nothing, crickets, right?
Jeez.
But they knew it wasn't sensitive enough. They keep pushing. 15 years later, it's now 50 years after it began, 100 years since Einstein first proposed these waves in the shape of space-time. It's a centenary. Some guys are working on a machine, experimentalists on two different sites. In the middle of the night, they decided they weren't ready for the science run. They're working to the wee hours in the morning. They get besides themselves. They decide it's time to go home. They mercifully leave the instrument locked. But they drive away, and it's still on, locked meaning ready for detection, not offline. And this wave washes over the site in Louisiana. It travels at the speed of light until it washes over the site in Washington State. And the instrument rings. And literally, they would listen to the instrument in the control room. Honestly, if it had struck a couple hours earlier, they would have been messing with the instrument too much to have made this detection. It's only the first detection. It's not like it was the only event in the universe. It was just the one that fate would have we were on a collision course with, right? And so it detects this ring. It's incredibly fast. It happens in milliseconds, and it's incredibly, you would say, quiet. The signal has to be drastically amplified, but it does happen in the human auditory range. The instrument is sensitive to frequencies of the ringing of space-time that are the same as like the piano. Which is, and the piano is such a great instrument because it's like the human auditory range. That's why all theorists learn. Musical theorists learn on the piano.
So what notes are they then? So does it go by mass? Like, if it's...
Yeah, just like you would think that the bigger the mass of the black hole, the lower the notes.
I see.
So there are some black holes that are so big and the collisions are at frequencies that we can't detect on Earth. And there is a project called LISA, which is proposed for space, which seems to be moving along.
So you have instead of 4 kilometers, the distance is much longer.
Yeah, you can have millions of kilometers. And what you're doing, you're not actually having them physically connected. You're having nodes, which are just floating instruments that shine lasers between them through the empty space around in probably a heliocentric orbit. So it's orbiting the sun.
So a big triangle orbiting the sun?
Big triangle orbiting the sun, yeah. I mean, each 3 of the instruments are separately orbiting.
Right. Yeah.
So, but the point is, I kind of liken it to an electric guitar. If you think of how an electric guitar works, you pluck a string. The string rings at a certain frequency, but you don't really hear it very well.
What do you mean?
You have to put the amplifiers.
Oh, that's right.
It's electric, right? And the amplifier records the ringing and plays it back to you, right? And that is actually kind of how the instrument works. It's like a musical instrument. It's detecting the ringing of space. And then it's going through this incredibly elaborate process of amplifying it for you and playing it back to you.
So now...
And you can listen to it.
Oh, really? So you go to a website?
Goes like, that's what it sounds like. It's called a chirp.
So tell me this, can you tell what it is by the sound of the chirp?
It's a great question. Mathematically, there are these really interesting papers that say, can you hear the shape of a drum? So from the frequencies of the ringing space, can you deduce like the shape of the drum? In this case, the analogy would really be the motion of the mallets.
I see.
The magnitude, the heft of the mallets, their mass, and their motions. And the answer is, I mean, there are some that you can't tell one from the other, but you can absolutely.
So have they simulated it? So you can go and listen to like, here's what this would sound like, here's what that would sound like.
So the first one they detected, they could very quickly, and they've been working on this also for decades, this analysis. You give me the sound and I'll give you the black holes. Wow. That's a hard problem. Many groups worked on that for a very long time. So there are different groups who try to get overlapping results. That's one way that they know that they haven't just totally biased and they have a real detection. And so what they came back with was, we just heard the collision of 2 black holes. They were each around 30 times the mass of the sun. One was a little bigger, one was a little smaller. So they're big. That's pretty big, 30 times the mass of the sun. And they caught them in their final handful of orbits. In a long life together. They might have been together for billions of years, slowly spiraling together, banging space-time, losing energy, coming closer, getting faster. By the time they're that close together, they could be traveling at 3/4 the speed of light, and it's happening really fast.
Okay, so you just said something. So when I was in graduate school, one of the guys who won a Nobel Prize in my department was for this end spiral of black holes due to, or I think it might have been even binary stars, because they lose energy by emitting gravitational waves. So those gravitational waves that are just emitted from the 2 things orbiting each other, we can't detect that.
No, and it's a really good question. We can detect that they're spiraling together. And we can use that to to deduce that we have calculated how much energy is being lost to these waves.
Yes.
And that was beautifully done. Nobel Prizes were involved.
Taylor
with
and
those.
Holst.
Yes. Right. And then one of them was a pulsar, right?
One of them was a
Holst-Taylor pulsar, right?
Oh, that's how they did the timing. Because it was so a pulsar is a neutron star that has a beam that points at you intermittently, so you see beeps. Beep, beep,
right. And it was an incredibly accurate determination, but they didn't directly detect the gravitational waves themselves. And you're saying, we can't detect those, and we cannot. They're way too weak. And this is part of gravity being weak. The Earth's pulling on us, but it's I can beat the whole Earth. I can jump, So gravity's really weak.
How would the frequency compare then? Would it be
too low, and the amplitude just undetectable.
So the volume and the pitch are outside of the range of our instruments.
Yeah. It's like, exactly. The volume is, your volume knob is way too low. This was, this sensitivity that we're describing is required because it's by the time it gets here, it's just, it's so faint. If you were floating near those two black holes when they were colliding, it is conceivable that even in the vacuum of empty space that your ear mechanism could ring in response.
Wow.
And you would hear it.
If you were close enough,
you would literally
it would move
hear it.
Wow.
Yeah. And your skull, being less given to squeezing and stretching, hopefully would resist, but you would hear it, right?
Because that's like,
yeah.
So here's something that comes to mind then. Mm-hmm. If these gravitational waves are emanating from these black holes colliding, are they escaping from inside the black hole?
That's a great question. They are not escaping from inside the black hole. It is ringing space outside the black holes. However, the final black hole has a mass that's less than the sum of the two black holes. The E equals mc squared energy. The mass that's lost is all pumped into these gravitational waves.
Wow.
So the 30-something solar mass black hole and the 20-something solar mass black hole, when they merge, that black hole is a little lighter than the sum of those two masses.
And are we talking
and all of that energy, E equals mc squared energy, as we know from nuclear bombs, right, is huge. So all of that energy was something like 3 solar masses of energy. It's enormous. Wow. And that means that event was the most powerful event human beings have recorded since the Big Bang.
Wow.
Now there have been others, but the power in it was more than the power in all the light from all the stars in the observable universe combined.
So how many of these things have they discovered now?
Well, now, if the instrument were operating all the time, kind of monthly.
Be like one a month we
detect.
Wow.
Kind of monthly. And the fact that they're so powerful, people didn't expect the black holes to be that big. So people worried, look, the black holes are going to be a few times the mass of the sun, only 10 times. That's a good kind of canonical 10. And so it's going to be hard to get anything loud enough to ring our instruments. They're going to have to be in real close, and we're going to have to get real lucky, but that's not what happened.
So we got
the black
dozens,
holes are big.
Do we have hundreds or thousands of times in terms of these collisions?
I would say, so in principle, they're happening all the time. They're just too far away. So we're kind of saying out to the distance we can detect. I don't want to say see, because none of it comes out as light. Right. All of this comes out in the ring in the black holes. It's complete darkness.
Jeez.
So it's one of the rare experiments in astronomy where we're not talking about a telescope collecting light. It's completely different.
So here's a question: if it's emitting all that energy, like 3 solar masses of energy, it may not be doing it in all directions equally. So could it just create a jet of gravitational energy and fly off?
You do have to think about the orientation of the orbital plane. So they're orbiting around each other, and there's a plane. The orientation of that plane relative to your line of sight or your line of detection in this case. And it does matter. It will change the signal. And so we also there's some ambiguity in trying to determine things like that.
Well, I guess the question I was getting at, though, is does the new black hole that formed, by the emitting all this gravitational wave energy, could that gravitational wave energy propel it to turn
it's a great
into
question.
a black hole that just shoots through the
it can
galaxy?
happen. So it shoots so much energy in one direction, the black hole starts to jettison.
Yeah.
Black holes can be cruising along. Yeah.
Holy cow! So out of nowhere.
Yeah, I mean, it maybe came in. It all depends on the orbits. Just like the mallets on the drum, if you swirl them around, it makes a certain sound.
Right.
It's very, eccentric, right?
Yeah.
If it's looping, coming close and going back out again, it will be very different. It'll be like a knocking. It'll get quiet. It'll bang. It'll get quiet, and then you'll hear it kind of bang, 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 bang.
Wow.
So yes, we can kind of determine its orbital motion as well as the masses of the original black holes. And maybe sometimes there are these funny things that can happen where a lot of energy goes off in one direction and the black hole just starts to kind of wander around the galaxy. But once it happens, it goes quiet. Once it forms,
so you get no more data.
So there's actually something really deep about this question of this ringing down. So when the event horizons merge like this bubble of ink and bobbles down and then goes quiet, that's because something very profound about black holes, and that is that they cannot tolerate any imperfections. And that's actually a deep point. So we've been talking about they cannot tolerate any imperfection. If you took Mount Everest and you tried to put it,
dated a black hole once in my youth. It was,
haven't we all? No. Or I was ever, I don't know. But if you put Mount Everest on the event horizon, it won't tolerate that bump for long. Okay, it has to shake it off. And one way to see it is kind of philosophically, to go back to my roots, which I disparaged, but and that is the event horizon says you can know nothing about the interior of a black hole. Right? You cannot know anything about it. If that bump remained, you would know more about it than you should be allowed to.
Oh, is this that so-called
very principle?
Black holes have no hair?
Black holes have no hair. The idea it can't have stuff emanating out of it, which would tell you, if you could trace the hair, it would tell you about properties on the inside. The event horizon really forbids the transmission of information from the interior of the black hole to the exterior. We've kind of established that in the beginning.
That's kind of by definition, right?
Right,
so
by definition. So that means that I can't come up to a black hole a billion years after its formation and deduce, that was a blue star.
Right.
Because that would mean somehow information was coming out of the interior. And no information could come out of that interior.
But why is that such a deep thing? Why?
Oh, well, okay. So there's several reasons why it's a deep thing. But in this context, I would say it's a deep thing because it means that there's something featureless about black holes. There are some things I can know about it. I can know its electric charge.
Right.
I can know its mass.
Yeah.
And I can know its spin.
Yes.
That's it. That's my whole list, right? And so the reason why that's so profound is it means it's not like anything else in the universe which can have flaws and features, right? So even a neutron star can have tiny, they're very tiny little features. I could say, that's my neutron star.
Right.
I put a flag on it. I went to the moon, I put a flag on it. The moon has this big crater. It has these, it's a specific moon.
Right.
And it's made up of this stuff.
Yeah.
It means that black holes are so featureless that they're closer to fundamental particles than they are to astrophysical objects.
So if I had
in that
two
sense.
black holes that had the same mass, charge, and spin,
you cannot tell their difference.
and I did the cup game.
There's no meaning to saying which one's which. It's
can't.
worse than saying, that's, I tracked it in my mind. There's no meaning to saying this black hole is mine or this was the one I marked. Or they are indistinguishable in the same way that an electron is indistinguishable from every other electron in the universe. And one electron's not a little bit heavier. You can't say, that's, that was my electron that I sloughed off this morning. They're so identical that they're technically interchangeable in a very profound way because we think that they're a fundamental particle of nature. So there's something fundamental about the electron. It's indivisible.
Right.
And it cannot be a little faster spin, a little heavier.
So there was this theory I heard that because electrons are indistinguishable, that means there's really only one electron in the universe. Have you heard this?
I have sort of, but
I don't know who made it. So
they're too busy for me.
If you choose three, you choose a set of three numbers to that really is one black hole. But
but it does suggest that black holes could be fundamental to nature. Now, this is why it's so profound. Whereas a neutron star is not fundamental to nature. It's made through a specific process.
Right.
It's strictly astrophysical.
Right.
It happens because of nuclear physics and these kinds of details. And neutron stars are all a little different from every other neutron star. They're slightly different.
Yeah,
They're more similar because they're getting on their way to black holes. It's harder to put a mountain on a neutron star, right, than it is on the Earth. So they're very similar. But the black hole being indistinguishable suggests it might be fundamental to the laws of nature. And that the fact that these huge objects, stars, made these big macroscopic black holes is crazy. But we should expect them in the Big Bang as well as little tiny microscopic black holes, because we should expect that they are fundamental to the laws of nature.
Okay, so let me tell you where you inspired my mind to go there.
Right, yeah.
Elementary particles are considered point particles, yet they have masses. So you can conclude, if you take that model seriously, that they have infinite density. And that's sort of like we say about the singularity of a black hole. So is it the case that if you tend to infinite density, you tend to being fundamental to the universe?
It's an interesting question. I think you would say, I think you're absolutely right. We think of electrons as point particles.
Right.
But you can't really exactly specify the location of the electron because of quantum mechanics.
Right, yeah.
And that kind of leads to a sort of fuzziness. It's not just the Heisenberg uncertainty principle, but even the whole thing's a little fuzzy.
What about the black hole? If it's going down to what appears to be
the center, but the horizon
is
pretty classical. It's not even, doesn't have to be quantum mechanics. It's so big.
So the when we talk about this fundamental black hole, where the only thing we can say are these three numbers, does that apply to the entire system, including the event horizon, or is that the whatever lies at the heart of the black hole?
I would say if you take that really seriously, what does it mean to say what's at the heart of the black hole?
To us,
it's behind
nothing.
The horizon.
Right, yeah.
So in some sense, even if, something really happened there, I threw an astronaut in, they had an experience, they were torn to shreds, and before they understood, what was really at the center. It was not a singularity, it was some quantum madness, right? To some extent, that doesn't matter.
This podcast is from the producers of Nova. Nova is supported by Carlisle Companies, a manufacturer of innovative building envelope systems. With buildings responsible for over a third of total energy use and energy demand on the rise, Carlisle's mission is to meet the challenge head on. Carlisle's energy-efficient solutions are built to reduce strain on the grid. For example, Carlisle's Ultra Touch denim insulation, made from sustainable recycled cotton fibers, delivers high thermal performance for improved energy efficiency while being safe to handle and easy to install. Made from 80% recycled denim, Ultra Touch diverts nearly 20 million pounds of textile waste from landfills each year. Operating nearly 100 manufacturing facilities across North America, Carlisle is working towards a more sustainable future. Learn more at carlisle.com. All right, so I'm going to give you some headlines. We're going to do a lightning round. 2 are true, and 1 is fake.
Okay.
And so if you can pick out the fake one, let's go. Physicists say many black holes seated in atmosphere could suck heat and fight global warming.
Is it true that physicists said that?
Yeah. So some physicists, they did their models, and they were like, listen, if we take these tiny black holes, we could use this to fight global climate change. Another one.
Okay.
There could be strange black hole moons that can indicate the existence of an advanced alien civilization.
Okay.
And the third one. Physicists propose a cheaper alternative to building a big accelerator. We could just use supermassive black holes.
Okay. I would say none of those things are true.
Well, these are real headlines. They may not be true, but which made the pages of
that
internet.
involves some social theory that I can't conquer. I can imagine the mini black hole was an actual headline, but I'm just imagining. what was the other one?
So we have
the advanced
sucking the heat out of the
civilization.
atmosphere using a black hole.
Right.
A black hole moon being a sign of an advanced alien civilization.
Right, if we could try to,
And using the supermassive black holes as particle colliders. But you got to put it in Switzerland. That's the only.
Yeah. I mean, well, I could say that supermassive black holes are probably particle accelerators.
All right, so you eliminated that one, and you were right.
Yeah, so because so black holes in general can, I mean, but this is actually real. Like we see this. We see enormous jets coming out of supermassive black holes. These jets are electromagnetic. They're literally like ray guns, where particles are shooting incredibly powerfully, high energy particles. It could be X-ray, literally like an X-ray gun, along these magnetic field lines. And we know that black holes can do that. So the irony of the darkest phenomena in the universe becoming the powerful engines of the brightest phenomena. Now, the particles aren't coming from inside the black hole.
Okay, but
they're
here's
originating
what I'm
from
getting at.
outside.
So this massive beam coming out of the center of a supermassive black hole, we're talking light years?
Yeah. The jets can be bigger than the galaxy in which they live. Yeah, you can see the jets. Hundreds of thousands of light years. Burst, like you can see them breaking out of the galaxy in cases.
Why didn't the Empire just use that?
Right.
Death Star, right? They could use the Death Hole.
Right, which leads us to the second headline. I mean, so it's not true in the sense that there has not been an advanced civilization that we are aware of that has made black hole moons. Let's just be clear. That
has not happened.
That has not happened to our knowledge.
That. But could we, just like people look for Dyson sphere signals.
Right. I suppose, gosh, if you figured out a way to collapse, I mean, a black hole moon is still pretty big. I mean, the sun, if it was a black hole, would be much smaller than our moon. Right? Much smaller than our moon.
But then if you put it at the moon's distance, Earth would orbit it. Just like it does now.
Right, exactly. So I don't know about that one. The mini black holes, I don't know. I mean, I can imagine a calculation. Let's see, how would this work? A little mini black hole would suck heat out because it would absorb stuff. Problem with mini black holes is they emit a lot, too.
There you go.
Through Hawking radiation.
There you go. So that was the false one.
So that was a false one. So they would be hotter. Then they would heat up the atmosphere.
Well, you know what? This is a terrible speed round because it's based on headlines.
Right.
And people would just write things to get the clicks.
They say crazy things. But that's, so the interesting thing about all black holes, we think Hawking radiate. They emit some quantum energy through this very subtle process that made Stephen Hawking so famous for its discovery. The bigger the black hole, the colder they are.
Right.
So the smaller the black hole, the hotter they are. So if I had a little mini black hole and I put it in the atmosphere, I'd be very likely to heat up the atmosphere.
That does not work with biceps.
And it would, right? And they also explode. They explode.
The tiny ones,
the mini
get
black
smaller
holes.
and smaller.
They explode eventually. So they're not going to do much good for cooling off.
All right. So one thing about relativity, about black holes to me is how they lie at the intersection, right? They're classical physics in size, but they're astronomical, cosmological objects. And they're in a realm of quantum mechanics in the sense of the horizon properties and the singularity, and they're relativistic. Right. So if you look at this deep connection between the quantum and relativity and cosmology and black holes, like where does that lead you?
So, I mean, we were just talking about Hawking. It is the same sense that black holes seem to be saying something fundamental about the universe. They also seem to be this one terrain that we have, just mathematically, pen and paper, on which we can explore gravity at its strongest, colliding with quantum mechanics. And you might have thought, as you just set it up, look, black holes, it's still a big object. Usually we think of them as macroscopic objects.
Yeah, exactly.
And so why am I worrying about quantum mechanics at 6 kilometers and not even a lot of curvature? Like I said, you could sail across the horizon and nothing bad happens to you. You're not in some crazy quantum realm. Well, it turns out, and that's why Hawking's discovery was so ingenious. It took just a little smidge of quantum mechanics to show that there was a very big problem. Okay, what I mean by a little smidge of quantum mechanics is this idea that even empty space has a little bit of quantum mechanics going on.
Right, yeah.
We've talked about Heisenberg's uncertainty principle, which says you can never precisely say exactly where a particle is located without losing a tremendous amount of knowledge, let's say in its motion, in its momentum. Well, that also kind of means you can never exactly say a particle's not there. Kind of led to these ideas. What does it mean to say, I 100% certainty say there is no particle there? This doesn't seem to be quite right, according to Heisenberg. And people started thinking about, oh, well, you know, you can have these sort of pairs of particles that come out of nothing. As long as they match enough to go back to nothing. If one's spinning up, the other better be spinning down. If one's positively charged, the other better be negatively charged. They have to equal the zero, the nothingness of empty space. So
nothing's changed.
They can't come out. You can't come out and like two positive particles. That can't happen, right? They have to cancel each other in all the ways you can kind of imagine. As long as it happens really fast and they go away again. And so in this room, I have no way of kind of capturing that energy. It happens really fast. But black hole can do something super sneaky. If this is happening, it's nothing special about the black hole. This is just quantum mechanics of empty space. It's nothing to do with the black hole being strong gravity or weak gravity or nothing. It's just that if this happens and one of the little particles in the pair ends up on the wrong side of the event horizon, the other one can't go back to the vacuum because now it's tainted. It has colors that can't go into the nothingness. You know, it has properties, it has charges, it's gone, right? It can't disappear into the vacuum, it lost its pair. Now that particle, which originated outside the black hole, is stuck, and it lives, it exists.
Stuck in existence.
It's stuck in existence. So the event horizon did something very, very tricky by not permitting, that its pair can never make it back out again. And so the one that was stranded can just sail off to the distance, and it looks like a particle is emitted. It looks like the black hole is radiating particles. Now this is a very, very, very tiny effect. For all astrophysical black holes, let me just clarify that point. So it looks like it's radiating particles. But the particle actually originates from outside the black hole. And it could be a photon. It could be an actual photon, or it could be a particle. But that lost it. They can all lose their pairs. And it looks like the edge of the black hole, just outside the event horizon, is radiating. And it looks like it has a temperature. And the tricky thing is that the particle it absorbed, what you think of as it has a negative momentum. Its momentum is directed with the whole space-time rotation in the same way that space and time interchange places, momentum and energy interchange places, and the black hole feels like it absorbed a negative energy. The black hole got a little lighter in the process. The black hole gets a little smaller. It seems to be radiating at this Hawking temperature, and it gets a little smaller. And eventually, gets smaller and smaller, and the process gets hotter, faster, more catastrophic. And the idea is eventually the black hole just explodes. So, like we talked about the mini black holes, just explodes.
So basically what you're saying is that quantum mechanics is caustic to black holes. It's corrosive to black holes.
They will evaporate away via this very subtle quantum process. And it's not extreme quantum mechanics. It's not quantum gravity. I don't need quantum gravity. Just a tiny little bit.
So one of the black hole people I saw speaking in an interview was Marco Ravelli. And he mentioned Carlo Ravelli. That's right. Carlo, Marco.
Yeah, Italian.
They're twins. He mentioned that they're bigger on the inside than they are on the outside.
Oh yeah.
So I've never actually solved the geometry inside of a black hole.
Yeah,
so how does that come about?
So black holes being bigger on the inside than the outside, the way I think of it, let's say you draw a circle, okay? We all are used to drawing a straight line to the center of that circle. So that's flat. And I know exactly how much area is contained in that flat geometry. But if it's curved, if I pull, if it's a little net webbing, and I pull it like a horn, like a trumpet, now there's a lot more area, right? Until you get to the center because of the curvature. So curved things can hide. That's a little misleading because I had to bend it into a third dimension, but yes.
Into another dimension. So that reminds me of the way they used to determine the areas of Euclidean figures with triangles inside of it.
Right.
So you can get the area of a circle.
Yeah. Everything we believe about areas and volumes inscribed
so
with
if I
boundaries.
Put a rectangle, a triangle inside of a black hole, the three angles don't sum to 180.
They do not.
Nah.
Yeah. And so it's non-Euclidean geometry. It's not flat geometry, and that's exactly it, that the space-time is curved. Now, I can't really do that with the black hole because I'd have to visualize it in curving in a different dimension. It's just very hard to do. You don't have to do the curving.
Yeah.
You know, we all see these pictures of these funnels that are meant to indicate black holes.
Yeah.
And what that really is an embedding diagram. It's not that the black hole, like this is an actual direction in space, which it bends into. That's not it. But it just helps you visualize. They're called embedding diagrams because they help you visualize the curvature as best that we can in our limitations of our visualizations. Our 3D minds.
Yes. Oh,
yes.
Boy.
But we do know everything we believe about the volume inside a sphere is based on Euclidean geometry, and it's not Euclidean in there. And so they can be very big on the inside. You know, you can have all kinds of strange things you can add to the interior of black holes just to noodle around.
Yeah.
We don't think nature does that when it collapses stars. But if I'm just playing games with general relativity, I mean, I can put all kinds of crazy things on the interior of a black hole.
Wow. So another thing about black holes that I heard that is one of those things you hear a lot as a person who consumes media, books about this stuff, is the idea that all of the information on the interior of the black hole can be encoded on the surface. It's like a hologram. You can get 3D information from a 2D surface, and then that somehow extends to the universe.
So what's going on here? So
yeah, exactly. Tell me what's going on.
So let's go back a little bit, because when these things explode, here's the problem. So they explode. So maybe that's just what happens, and fascinating. Wow, interesting. Black holes evaporate away and they explode. Big deal. Or it's a big deal because it said there was now a fundamental paradox between Einstein's predictions about black holes, or they weren't Einstein's, but in the context of Einstein's theory, versus the predictions of quantum mechanics. Because I've told you, you can know nothing about the interior of a black hole. You can know nothing about it. So that means that all of that radiation that escaped from the black hole has no information about what went in. Now, what's so bad about that? You could say, you know, when we talked about the event horizon before, well, so what? We can't know what's on the inside. I'm okay with that, as long as it's still there.
Right.
Why does that matter to me? Because quantum mechanics says you cannot destroy information. So if I accept, even if you haven't studied quantum mechanics, if you just take people's word for it, that the entire theory is structured in such a way that you cannot lose information.
Right.
Okay.
Yeah.
Now, general relativity says the event horizon is structured in such a way that you cannot have that information that you want. You cannot. Okay. It is behind the event horizon.
Right.
And all this radiation that came out of the black hole over billions of years could not have had a single bit of information about all the quantum particles that originally entered.
Right.
Now, I don't mind that as long as they're always locked inside. But once you yank the curtain up, when this thing explodes and the event horizon is yanked up, where did all that quantum information go?
Right.
Now I have a real problem. Quantum mechanics is wrong, or something's wrong about the predictions of general relativity. Somehow the information does get past the event horizon. Okay?
Has this been resolved?
Ongoing since the 70s. Okay. At one point, Hawking made a bet that information was lost. It went back and forth. The quantum people held strong, said quantum mechanics won't give. And where we are now, after those 50 plus years, is the belief that in fact the information will make it out in very, very subtle ways, but it's very subtle.
Interesting.
Very subtle. Now you talked about holography, and it all comes back to this idea.
Yeah.
But it comes back to where the information maybe actually gets stored. So there's lots of different attempts people have made. Or entanglement between the interior of a black hole and the exterior of a black hole.
Oh, wow.
And maybe the Hawking radiation is quantum entangled. This is how crazy it's gotten. With wormholes.
Oh, the ER equals EPR?
Yeah, so the idea that you can entangle across the event horizon with a wormhole, allows you to cheat the event horizon a little, so that now the radiation that escapes was entangled with something on the interior of the black hole, and thereby can have information.
So we use the phrase quantum entanglement. Would you mind unpacking that a little bit?
Yeah, quantum entanglement is pretty tricky. So we can think of, I often give the wishbone example of entanglement.
Okay,
so,
I don't know that one.
Do you know
I know what a wishbone is.
Yeah, you know what a wishbone is, right? So you take as a
Yeah.
kid, you each hold at some part of the poor turkey,
Yeah.
and you break it at Thanksgiving, and one of you gets the big piece, and one of you
That's
gets
right.
the small piece. It's
Yeah.
never even.
Right.
And so that's a non-quantum entanglement. Suppose we didn't look at the result. We break it, we don't look, and you put yours in your pocket, I put mine in my pocket.
Right.
I look at mine, I have the big piece, I know you have the small piece. Also
Right.
not quantum.
Right.
Okay?
Right.
The
But
quantum
observing
experiment,
yours lets you know mine.
I immediately know yours.
Right.
The quantum one's drastically more mysterious. In the quantum superposition, we break entanglement, we break the wishbone, we put it in our pockets, but it hasn't assumed a definite state yet. I have the big one, you have the small one, plus I have the small piece and you have the big bone. And so
we both have a combination of big piece, small piece,
Right.
until one of us looks.
Right. And so, but it's literally in a superposition of those two states. It has not fully, sometimes we say collapsed,
Right.
to be one or the other of those solutions. It is actually both.
Right.
And if I very precariously travel to Andromeda, another galaxy far away, quantum mechanics is so delicate, it's hard to maintain that superposition.
Right.
So maybe it just gets hot in my pocket, or I actually bombard it with particles to see what's going on.
Yeah.
Maybe I shine light on it so I can literally see it, right? I will disturb the superposition,
Right.
and it will either be the big piece and I've won, or the small piece and I've lost.
Right.
But instantaneously, your piece has assumed the proper pair.
So
that
it's
it
no
must
longer.
be. It is no longer in a superposition.
Yours was in this state of bothness.
Yeah.
Mine was in the state of bothness that we call superposition.
Right.
We're 2 million light years apart.
Right.
You decide to look at yours.
Yeah.
And so it goes out of bothness state
Right.
and
Yeah.
becomes a single state.
Yeah.
And mine,
Yeah.
2 million light years away,
Yeah.
does the same thing and becomes the
Yeah.
correct. Wow.
Right. So Einstein talked about this as an argument for why quantum mechanics must be wrong. He was trying to say it's wrong, it's absurd. That cannot be. First of all, it seems as though information traveled faster than the speed of light.
Right.
And second of all, it's just action at a distance, which he'd been trying to cure since he first thought about curved space-time. Didn't want the Earth pulling on the apple from some great distance. Didn't make sense to him.
Yeah.
It was spooky action at a distance, and now it was back.
Yeah.
And he had fixed this already, you know. But it seems to be just the way it is. Now, you have to be careful about information traveling faster than the speed of light. When you look at your piece, you don't know that I've performed my experiment faster than the speed of light.
Right.
You don't know that you're not the one who collapsed the wave function.
Yeah.
For you and I to determine which one of us was the one that collapsed and caused this to happen, we'd have to get on a phone, send a light signal. We would have to communicate slower or at the speed of light.
Right.
And so no classical information is ever communicated faster than the speed of light.
Right.
But quantum information seems to be able to do this.
Wow. Yeah.
So the entanglement is this kind of, the outside particle in the Hawking radiation comes out and it's the big piece. It tells you that the small piece is on the inside. You just learned something about something on the inside of the black hole.
Ah, okay.
So that's how entanglement allows you to get information about
I
what's
see.
inside the black hole.
Yeah,
It's
yeah. So something on the
very
outside
clever.
could be entangled with something on the inside, and therefore,
Right.
by making a measurement of the outside,
You
can
know
get
everything about what's on the inside.
All these years.
All these years. Now there's a whole complicated story about entanglements, because I thought my particle had to be entangled with the Hawking, its pair,
Yeah.
because same reason, they had to be perfectly matched to go back to the vacuum.
Yeah.
So it can't be entangled with the pair and be entangled with what made the black hole and the quantum particles that had fallen in long ago. So it wasn't that quick a solution. They've really struggled. And that's why wormholes start to come in. They're like, well, maybe particle on the outside is the particle on the inside because they're connected by a wormhole. It gets pretty wacky.
Yeah.
So I'm not going to tell you that there's a pen and paper solution where I can calculate it for you and say, see, I'm tracking this quantum bit.
Right.
And I can show you how it came out.
Right.
And how somebody on the outside captured it and reconstructed the piece of wood that fell inside incendiary, and I rebuild it.
So you can get information, but not full histories.
Nobody knows how to do it yet.
Okay.
But why do they think it's plausible? They think it's plausible because of these really subtle arguments around holography.
I was just talking to my kid about this because we were sitting around. I like to build a fire at night sometimes, right?
Yeah.
And I was like, yeah, he was asking me about where does the wood go, right? And I was like, yeah. So, if you add up all the ash and capture it and weigh it, capture all the smoke and weigh it, and capture all the gases, it'll weigh the same as the original wood.
Right.
But now the question becomes, if you were to give someone, here's a bag of ash, here's a bag of smoke, here's a bag of gases, what did I burn?
Right. Yeah.
You can imagine they could reconstruct that. Oh, you burned an oak log.
It's even stronger than that. If you had carved your initials on the wood, in principle, I should be able to reconstruct even that detail.
Oh, geez.
Everything. I must be able to reconstruct. Now, of course, nobody could do it in practice. So why do we think that? We think that because we think that this information isn't lost. That's exactly it.
So you really took things to a different level on me, right?
Yeah.
Because now, that's like a cosmetic feature as I think of it. It's not...
Right, but it's still information and how the atoms were arranged relative to each other.
Wait, even their arrangement? So I can say whether it was a cube or a sphere of wood?
Right, in principle.
Or a cylinder?
And if it was an encyclopedia.
Or what if it was spinning as it was burning?
You should be able to reconstruct the written, if Shakespeare, if Romeo and Juliet was written on the page, you should be able to reconstruct it. And you burnt a piece of paper.
Man.
But this is how seriously people take the idea of information. Now, you can't do it. So the idea would be, okay, if I'm sitting outside the black hole and I have these stations and I'm collecting all the Hawking radiation, I should be able to do what you just said I could do for the burning wood and reconstruct all the information in it. But the event horizon says it has no information in it. So I don't need to be able to do it in practice.
Right.
I just need to believe that the information didn't disappear from the universe.
Right. And then quantum mechanics is satisfied.
The quantum mechanics is safe.
It's safe.
Yes.
Yeah. So you mentioned that black holes are like fundamental particles, like electrons, right? They have this description that's nicely, neatly packaged, and they're indistinguishable.
Why is that a big deal?
Why is that a big deal?
I think it's a big deal because we often talk about how black holes are dead stars. And that's true. Some stars, if they're very, very heavy at the end of their life cycle, when they run out of nuclear fuel, will not be able to resist this catastrophic collapse.
Right.
And they'll just keep falling. We talked about it's hard to crush things. That's one of the only ways anyone's ever thought of to make a black hole. It's an entire star
crushing.
collapsing without the nuclear fuel resisting the collapse. So we often think, okay, black holes are these dead stars, collapsed stars. But what we're realizing is that's just one way nature figured out how to make them.
Right.
And it's just a way nature figured out how to make very big macroscopic black holes. Because if they're fundamental particles, they should be made little tiny black holes, like in the Big Bang. Same time electrons are made. Matter is made in the early universe. Hydrogen in our body comes from the early universe.
I would argue that when we talk about these elementary particles, what we say is that they are quantizations of a quantum field. Right. And so we think of there's an electron field and there's these quark fields. So would there be a black hole field?
Well, that's a really interesting question. I think you would say there's a gravitational field and there is a quanta of the gravitational field, the graviton, the force carrier, of the gravitational field. That's really interesting. But are they quanta of indivisible, the smallest unit of mass in some sense, a very primordial black hole made in the Big Bang, it would actually be heavy for its tiny size. That's the whole thing about black holes.
But aren't those the
right?
ones that radiate? The ones that
Oh, it's a
evaporate
really
and explode?
right. It's a really good question. So there's
Yeah.
different gradations. You could make, because black holes, unlike electrons, can come in different masses. It can come
Right.
in all masses.
Yeah.
So in the early universe, the thinking is really, well, you make primordial black holes that they are very small, and yes, they explode. That's exactly what people think happened to them. And so we look for signals of these firecrackers from the early universe that
Right.
could be exploding black holes. And so people do take seriously that black holes were formed in other ways than just collapsed stars.
So if they are formed in a Big Bang, these microscopic black holes, and we can get information out of them, then could they be a way of
Well, they could tell us,
probing?
yes, they can tell us about the Big Bang, as
Yeah.
can all the particles, right, from the
right,
early universe.
nucleosynthesis,
Right,
hydrogenization?
but the black hole is playing a special role in terms of understanding the fundamental laws of the universe, because it really is unique in a terrain where gravity and quantum mechanics are really fighting for control,
Wow,
fighting for
wow.
dominance, right? So it is really the key, and by terrain, I really mean calculations. Nobody can do this in astrophysics yet,
Yeah.
right? Nobody can measure this in real objects out there physically. So this is just pen and paper.
Yeah.
But it provides, it's giving us all the clues. It's showing us the way.
Wow.
Right? Because it's so restrictive,
Yeah.
so constrained, and yet it's telling us all of this incredible directions to look in, to understand how quantum mechanics and gravity came together. And if we do understand it on the black hole, we'll understand the Big Bang.
So you're truly researching at the frontier. You're at the edge
Yeah.
of understanding.
Well, I right now, I'm not really right now. I'm looking more at extraspatial dimensions these days. Yes, I've done many
Interesting.
years of just black holes for
Right.
various properties, but as engines, as electromagnetic batteries, we have
Wow.
as making black hole pulsars. Just a phase where they could look like a pulsar but be a black hole pulsar.
Right,
but
right.
these days I work a lot in extraspatial dimensions, and the idea that we were joking about our three-dimensional selves, but maybe not. Maybe there are these extra dimensions, and we are just bound to three for reasons that we try to understand.
Wow.
And that is actually what I work on every day these days.
That is amazing.
Yeah. So,
So is it in the context of string theory or?
well, it's not string theory. In fact, extra dimensions have been around for 100 years. As soon as Einstein started working on space-time and taking seriously that space and time were relative, people started asking, well, like, why three? Why three space in one
Right.
time?
Yeah.
And in fact, there was really exciting ideas that if the universe had higher dimensions, it would explain electromagnetism as which is one of our fundamental forces, as connected to gravity in a fundamental way. It would unify them together in a fundamental way. That the extra dimensions could actually make a mode of gravity look like a photon or something like that.
Holy cow.
So the extra dimensions as part of unification long predates string theory. And,
Oh, wow. Okay.
And it might be that dark energy is energy trapped in the extra dimensions. It might be that dark matter are excitations of the extra dimensions. It could explain a lot, or it might just be that they're there.
So talk about the edge of an understanding. Like,
Yeah.
You're like, let me just take so it's not motivated necessarily by we've observed something. It's more like Einstein did it. I'm dealing with these concepts and I'm seeing.
We have this intuition. We started looking at some things because when you move around in the extra dimensions, sometimes things can come back rotated in a profound way. I can set a left-handed particle in and it can come back right-handed.
Okay.
Very strange things like that. And so there's reasons you start noodling around, but sometimes you don't know what you're going to find.
Right. Yeah.
Absolutely. But I'd say that my work is unified around space-time themes. That is almost always, so it sounds very different. The Big Bang, black holes, extra dimensions, gravitational waves, but they're all really space-time thinking.
Yeah. I've done the same trick in my career in the sense that I'm like, okay, I can compute, I understand plasmas, and I know how to experiment. I can go to all these different areas. And
sometimes you just have to stay agile.
Oh, absolutely.
Right.
Well, I
So,
get bored personally. I can't.
I like to be a student again. So every few
I love
years,
it.
I have to be a student again.
I like to feel like everyone in the room knows more than me.
Oh yeah, I mean,
Yeah.
my collaborators now they can dabble in string theory. They're more than dabble. They're all really accomplished in string theory as well as other areas of particle physics. So it's just a pleasure for me to.
Well,
to
this
be with them.
interview has been a pleasure for me. Thank you so much.
Thank you so much.
for
Thank you.
expanding my event horizon.
Thank you for having me.
Awesome.
Pleasure,
Can't wait
friend.
till next time.
Yeah.
Hey.